Math 2414, Series, Video 6, an extremely useful series. This series will show up later in this chapter, but I figured exposing you to it now is going to make it. It's actually a pretty easy one to figure out. It starts with the absolute value of x less than 1. Then let's look at the infinitely long polynomial 1 plus x squared plus x cubed plus x fourth plus, etc., etc., etc. As a polynomial, it goes forever. Normally, when we write polynomials, we write the highest power first, go all the way down to the constant. But since this has no highest power, our only choice really is to start on the other end, start with the constant, and then the first power, second power, third, fourth, etc., etc., etc. Oops, don't look at that yet. Don't look at that. All right. So as an infinite series, notice that this is a geometric series. It's a geometric series by definition because its terms form a geometric sequence, which means that the ratio of consecutive terms is the same. If we look at the ratio of the first two terms, x over 1 is just x. If we look at the ratio of the next two terms, x squared over x is just x. And the same thing if we go to the third and fourth terms, x cubed over x squared is x. So this is a geometric series, and the common ratio is x. Ratio is x. And the absolute value of the ratio, which would be absolute value of x, we're assuming is less than 1, which means as a geometric series, this converges. And like any geometric series, it will always converge, or any convergent geometric series, it will always converge to the first term over 1 minus the ratio. Well, ratio, not ration. Well, the first term is 1 and the ratio is x. My phone's blowing up. So the first term is 1 minus the ratio is x. This is a very important series. Again, this will show up many, many, many times in the near future. It's so important that I think it deserves to have a box drawn around it, and let's do purple. Excuse me. Of course, the one kind of is trying to break free there. All right, so this is our first instance of an infinitely long polynomial converging under the right conditions. So in function notation, we could say that if f of x equals 1 over 1 minus x, then we can rewrite it as this. If the absolute value of x is less than 1. If x was bigger than 1, it wouldn't make sense. For example, if x was 2, then we would be adding 1 plus 2 squared is 4 plus 2 cubed is 8 plus 2 to the fourth is 16. But if we put x equals 2 down here, we would get 1 over negative 1, which is negative 1. So it would be silly to say that all these add up to negative 1. So keep in mind that this infinite series is only valid when the absolute value of x is less than 1. Now, how can we use this? Well, in the long term, what we're going to eventually do is take things that we can't integrate and turn them into things that we can integrate, even if it's an infinitely long series of things that we integrate. Granted, we can't integrate that. If you think about it, it's just a real quick use. But let's take a look at this one and see if we can write it as an infinite series. The trick that we're going to use, it's not really a trick, is to remember that 1 over 1 minus x is equal to 1 plus x squared plus x cubed if the absolute value of x is less than 1. Well, if we're going to take advantage of that piece of information on this function, then we need to fix two things. We need to fix the 4 on the top because it needs to be a 1, and we need to fix the 2 down here because it also needs to be a 1. The fact that this is or is not an x is irrelevant because the thing here is a variable and it can assume any value that we want, even if it's a different version of x or any letter. But 1s are constants, which means that we're going to use this formula, we have to trick out this function so that there is a 1 on the top and a 1 on the left side of the subtraction sign. So how are we going to do that? Well, the first thing I would do is fix the 2 and make it a 1. Now, how can we do that? By multiplying both sides of this fraction by the reciprocal of 2, also known as 1. By doing that, it'll turn the top into 2, and when I distribute the 1/2, it'll put the 1 on the left side of the subtraction sign. And that'll give me 3/2 x, or 3x over 2, whichever you prefer. Now, how can I make the 1 show up on the top? Well, I can't multiply both sides by 1/2 again. That would destroy the one that I just created. But being the only number on top, I can pull it in front of the fraction. 1 over 1 minus 3/2 to the x. So now I've got my function resembling the correct form. In other words, I've got a 1 where I need it, there, and down there, which means I can now take advantage of what we know about the thing in red at the bottom, that the thing in red is equal to 1 plus x squared plus x cubed if the absolute value of x is less than 1. So how would we do that here? Well, we would just replace the x with 3/2 x everywhere we see it. Get rid of all this on the bottom for now. And so this will equal, got to be erasing. This will equal 2 times. All right, now that it's in the correct form, we just have to start adding powers of the ratio. Our ratio, by the way, is 3/2 x. Remember, I was just thinking of something. Remember that our sum is the first term over 1 minus the ratio. I was thinking I could have left the 2 on the top, but let's go ahead and pull it out for now. All right, so inside the parentheses, the number on top is the first term, so that's 1, plus the ratio, 3/2 x, plus the ratio squared, plus the ratio to the 4th power, third power, plus et cetera, et cetera. At this point, we technically have what we want, which was our infinite series. But I'd really like the power to be on the x, so we're going to distribute the power. 3/2 x plus, and I'm going to write it as 3 squared over 2 squared x squared. I could write that as 9/4, of course. 3 cubed over 2 cubed x cubed plus. But there's a reason I wanted to write it like that, because I'm going to try to write this in sigma notation. How can we do that? Well, all we got to do is figure out what the nth term looks like and set up our sigma. Our nth term would be 3 to the n, x to the n, 2 to the n. And now that we've exposed our nth term, we can write this in sigma form. Let's clean this up, and then we'll wrap up this problem and this video. All right, so how are we going to write the thing on the inside as a sum? Actually, not that hard. We already know what the nth term looks like, so that can be our argument. 3 to the n, x to the n, 2 to the n. And what is the sum starting at? It's going to infinity, that's pretty clear. But what should we let n equal in order to get the correct first term? The answer is 0. So now we've rewritten our original function as an infinite series. And if you wanted to, because of the distributive property, you could distribute the 2 on the outside into the sum. We're actually using a property I haven't defined yet. And if we move that 2 to the first power inside, then we can cancel one of the 2's in the denominator. We make it 3 to the n over 2 to the n minus 1 times x to the n. Put parentheses in. That long fraction bar is bothering me. All right, so now we've successfully written our original function, which was this guy without all the red, as an infinite series. We're going to be doing this a lot more in the future. I just wanted to introduce it to you now. The key thing you need to take away from this video is that if the absolute value of x is less than 1, then that infinitely long polynomial, sums of powers of x's, coefficients are all 1s, is equal to 1 over 1 minus x.